We have just seen in the previous videos how to demonstrate the Hohenberg-Eckert theorem, thanks to which we can say that every observable in the ground state is a unique functional of the electron density. We want to end now this section by pointing out some consequences and discuss some issues related to the Hohenberg-Eckert theorem. Of course, this might seem a complicated task. After all, since 1964, the number of discussions, issues, and different ways to look at the Hohenberg-Eckert theorem has exploded. It is enough to Google Hohenberg-Eckert theorem to meet with hundreds of thousands of hits. Here, for the purpose of this course, we would like to point out some obvious and immediate consequences of the theorem. Let's start with something that was already discussed in the original article, the total energy. The total energy is, of course, a particular measurable quantity, and the operator is just the Hamiltonian. But in particular, for the ground state total energy, we also have the variational theorem that says that if we search among all possible wave functions, the one that would give us the smallest number, the ground state at total energy, is the ground state wave function. And since for the Hohenberg-Eckert theorem there is a one-to-one correspondence between wave functions and density, it is the ground state density that corresponds to the ground state wave function. This minimization then can be done directly on the density itself. We can search among all densities. The one that minimizes the energy functional is the ground state density and corresponds to the ground state total energy. This is very often called second part of the Hohenberg-Eckert theorem and illustrates its most direct consequence. But it tells us more than that. It clearly shows a practical way, a variational procedure, to find an observable as a density functional. In fact, rather than using the variational theorem in the realm of all the possible wave functions that live in a 3n dimensional space and for which the energy surface can be enormously complicated, thanks to the Hohenberg-Eckert theorem, we can restrict our search to the realm of the densities that live in a much smaller place and for which the search can be conducted in a simple way. For a given density profile, let's call it N1, we will have a certain total energy E of N1. For another density, N2, we will have another energy. Same for N3 and N4, and for as many densities required to figure out the shape of the energy surface. We can now evaluate the minimum of the total energy, which constitutes the ground state total energy, in correspondence with the ground state density N0. This is not exactly how DFT works in practice, or at least in the majority of applications, but you can clearly see a possible approach, a possible working procedure. The first problem we see here is that we do not know how to connect the density to the total energy. In short, we do not know the functional. Let's see this more in details. Formally, the total energy can be written in terms of the expectation value with the full many-body wave function. In it, we have an explicit functional of the density related to the external potential, because it is a one-body operator, and we have the parts related to the kinetic and electron-electron operators, and these two are unknown. They are also, as you can see, independent of the external potential. We call this term the Hohenberg-Eckert functional, or the universal functional. Since it does not depend on the external potential, it is the same for every system. We do not know this functional. Of course, if we were able to evaluate the total energy for a certain set of external potentials, we could invert this equation and find the universal functional F. Attention here. This implies the knowledge of the total energies for all possible densities N of R, all of them. But if it's the case, we will have a full knowledge of the universal functional that could then be applied to all systems. Clearly, you see here that finding the universal functional for all possible densities implies that many external potentials have to be considered and solved. to explore the full range of possible densities. It doesn't seem a viable solution. And in fact, it is not. Except, well, if I mention this, it's because today an entire branch of researchers is devoted to exactly find this mapping, but not with the clever approximations or models and analytical solutions, but really brute force using machine learning. We will not say more about it now. What we need to emphasize now is the outcome of the Hohenberg-Economic theorem. The functional of the density, if it exists, it is unique. So for one potential, one system, one density. But it is completely unknown. I'll let you think about it a moment because I just added an important info here. One moment ago, I said that if the functional exists, it is unique. And in fact, the Hohenberg-Economic theorem is a uniqueness theorem. It never says that such a functional should always exist. Lots of analysis have been carried out in the 70s and the 80s about the existence of the functional, the conditions, the constraints for such existence. In mathematical terms, we talk about the V representability. This is something that goes a little beyond the introduction to DDFT we want to give here, but it definitely worth mentioning. So, what is this? It is very simple to state. Let's say we have a reasonable density. For reasonable, I mean a function which is positively defined, and it is normalized to the number of electrons. So, it is a possible density profile for a system. And now the question is, given this density, is it possible to find an external potential that leads to this density? Or, in other words, given a density profile, is there a system that has this density? Now, I know what you're thinking. This really seems a mathematician problem. One of those little details about the existence under certain conditions that we never care about it, right? And I will tell you more. If you think about it, why should we care about possible densities that do not come from a specific external potential? In fact, all physical densities, since they exist, they are there because they come from a specific system. So they are certainly related to some external potential. Why should we care about those probably few densities which are not connected to any physical situation? Well, there are at least two important reasons for that. Firstly, from the mathematical point of view, it is always very important to know the limits and the validity of a theorem, the possible constraints, and see if generalizations are possible. And secondly, even from a more practical point of view, if one searches for the density for which we have a minimum, well, it is crucial to know if and when a density represents or not a real system. So the research about the V representability was a very important one, and starting from the 80s, produced very fundamental and useful results, mainly with the works of Levy, Lieb, and English. Even if we do not go here into the details of such works, but we suggest to have a look if interested, we would like to point out that this branch of research connected DFT to even more general concepts like ensemble V representability or N representability, and it led to a clarification and a generalization of the Hohenberg-Economic theorem, for example, by removing the original constraint of non-degenerate ground state. So again, have a look at those articles if you are inclined to these more fundamental and mathematical aspects. We stop here for the moment. Next week, we will see more in details how to use DFT. After all, even if now we know that every observable is a functional of the density, we still do not know the functional, and we do not know the density. So stay tuned. Goodbye.